So we are talking about the free particle in quantum mechanics, right? So last time we argued based on a very simple construction of adding two waves, two sinusoidal waves. We introduced the concepts of group velocity and phase velocity. And we also showed that in principle, using the idea of destructive interference and carefully choosing how you choose to add and subtract these waves, we can construct something out of a whole bunch of waves that is actually a localized object, and we call this object a wave packet. Okay. So mathematically, as I talked about last time, it is not possible to do this with just adding 2 waves or 3 waves or 5 waves or 7 waves. You actually need an infinite number of waves. So the linear superposition actually becomes an integral. So out of a whole bunch of waves, I can simply add the waves, and I will assume that the wave number k is now a continuous parameter. I will say that this is a function of k e to the I kx. Okay, now I'm using the e to the I kx representation because it is a lot more useful for me to do this instead of looking at cosines and sines. But one might equally well think of this as a, two integrals, one over cosine and one over sine, but mathematical manipulations are much easier with e to the I kx. Okay. Now, if I want to understand how this wave propagates in time, of course, I simply need to tag on the time dependence, which, as you know, is just e to the I omega x. Sorry, this is a function of x and not k. Yeah, I'm integrating out k. So psi of x comma t would be integral dk g of k e to the I kx times e to the minus I omega t. Okay, now in this class, I'll be concerned with the first formula up top. I'll add the time dependence in the, hopefully in the next lecture. Okay. Now, the last time when I asked you guys if you guys are comfortable with Fourier transforms, a couple of you said yes, but a bunch of you said no. So I think before I delve into the treatment of wave packets and trying to understand the uncertainty principle and things like that, it might be useful to spend a few minutes discussing about the first integral. Okay, how does one understand the first integral? So can I assume that everyone here has seen Fourier series before?
Yes, sir.
Yes, sir.
Okay, in other words, this is might be a better question. Is there anyone here who has not seen a Fourier series before? Okay, Sachin says no. So Sachin, you have not seen a Fourier series before?
Yes, I haven't seen it.
Okay. All right. So I'll spend 2 minutes telling you what a Fourier series is, and then I will discuss the generalization of this Fourier series, and I will introduce the integral number 1. Okay, or I'll call it by something. Formula A. Okay, I will actually make it rather obvious in terms of the logical extension of what you know by Fourier series. So I will use a different color. Let me put a line over here. Okay, now I'm going to talk about Fourier integrals for some time. Fourier series and Fourier transforms. So this is an aside from the main point of the lecture, but it's a very, very important aside because you will be using this very many times in your study of quantum mechanics. So even if you know it, please pay attention. It might be a good revision of sorts. Okay. So let us first try to recap what a Fourier series is. Let us say that I have some kind of a periodic function. Okay. How do you understand a periodic function? A periodic function is something whose value repeats after some intervals of the argument. So let us say that you have a function of x such that if x of, let us say, x plus 2a is the same as f of x, then this function is periodic with a period of 2a, okay? Or it can be the time domain, f of t equals f of t plus some t prime, okay? Or it can be an angular domain, f of theta equals f of theta plus 2 pi. So all these are periodic functions. They are periodic in some kind of a variable. In this case, I'm choosing x because that is what we are studying in quantum mechanics. So I'm choosing a function f that repeats itself after every 2a intervals. Okay. For example, this is very important in the study of what are called periodic potentials in quantum mechanics and the study of Bloch's theorem, as we will find out later. Now, the point is that if you have a periodic function, I can expand such a periodic function in cosines and sines. I'll first write this down and then I will justify it. So I can write this function f of x as n equals 0 to infinity an cosine kx plus n equals 0 to infinity bn sine kx. Okay. Now, how is this related to that? Well, cosines and sines are telltale periodic functions, right? So I can always impose the periodicity of f of x onto the cosine and sine functions by appropriately choosing the expansion coefficient, by appropriately choosing the argument kn. Okay, I will tell you how to choose the argument kn. Another way of looking at the same thing is as follows. Using your knowledge of vector spaces, you can assume that we are living in some kind of a space in which the cosines and sines are the basis functions. So I'm expanding an arbitrary periodic function as a linear superposition of the cosines and sines, which are the basis functions. Whichever way you want to look at it, it's exactly the same thing mathematically. Okay. So how will I choose my value of kn? Well, I want the function at x plus 2a to be numerically equal to the function at f of x, right? So if I evaluate f of x at x is equal to 5, then, and let us say that I get 3.2, then f of 5 plus 2a should also be equal to 3.2, right? That is what the statement means. The statement means that the numerical value of the function at x and the numerical value of the function at x plus 2a are the same for some fixed a. Okay. So if I want f of x plus 2a to be the same as a, then what is f of x plus 2a? F of x plus 2a should be equal to, or I will write it in one step, should be equal to f of x. And this would imply that cosine kn x plus 2a should be equal to cosine kn x. Okay, because the ans don't change, they are just constants. And sine kn of x plus 2a should be equal to sine knx. Okay. Now, the solution for both of these is actually satisfied by the following choice. Take the first guy. I'll take the first guy. So, cosine knx, cosine kn times 2a minus sine knx, sine kn times 2a equals cosine knx. So for this equation to be valid, now I cannot choose sine knx to be 0 because that will change depending on where I am, right, for various values of x. But I can choose things such that cosine kn times 2a is 1 and sine kn times 2a is equal to 0. If I choose these values, then this equation is satisfied. So my choice is cosine kn times 2a is 1 and sine kn times 2a is 0, right? And these can both be satisfied if the argument kn times 2a is 2n pi. It cannot be n pi, mind you, because cosine n pi is not necessarily 1. Cosine n pi is minus 1 to the n, because cosine pi is minus 1, cosine 2 pi is 1, cosine 3 pi is minus 1, and so on and so forth. But if you want it to be identically equal to 1, you should choose cosine kn times 2a to be equal to 2n pi. And obviously, sine 2n pi is always equal to 0. So this constraint satisfies both of these conditions. this would imply that my kn's cannot be arbitrary, but my kn has to be n pi over a. Okay. Now, if you substitute this in the expansion, f of x would be equal to n equals 0 to infinity an cosine n pi x over a plus n equals 0 to infinity bn sine n pi x over a. Okay. This is why I chose the period to be 2a and not a. If I choose 2a, my arguments turn out to be n pi x over a. So I don't have to carry factors of 1/2 all. Anyway, now notice that I can also write this in the exponential notation by noting that cosine k and x can be written as 1/2 of e to the I k n x plus e to the minus I k n x. I realize this might be elementary for some people, but it's still useful to understand thoroughly. Kn x minus e to the minus I kn x. This is just the Euler formula applied over and over again. So I can write my f of x now as n equals 0 to infinity. Now notice that I can club this in terms of e to the I kn x and e to the minus I kn x, right? So I can write this as 1/2 an plus bn over I e to the I kn x plus n equals 0 to infinity 1/2 an minus bn over I e to the minus I kn x. And this is some function of an and bn, which is just some other constant. So I'll call this constant some value an prime, and this I'll call some bn prime. So in terms of the exponential representation, I can write my f of x as 0 to infinity an prime e to the I kn x plus n equals 0 to infinity bn prime e to the minus I kn x. And then if you stare at this, you realize that you don't really need two sums. You can just convert this into one sum, but you can let n run from both positive and negative integers. Okay. N equals positive integers. Remember that kn is n pi over a. N positive integer will give you all the first term, and n negative integers will all give you all the second terms. So I can collapse these two into one series with n going from minus infinity to plus infinity of some Cn e to the I n pi x over a. Okay. So this is the.
So can you repeat this?
So what is the first step? The first step, so this equation tells you that, so suppose if I write this out, this is f of x equals, now let's write out a few terms, right? If I write out a few terms, that should be obvious to you. So a0 prime times e to the 1 plus a1 prime e to the I pi x over a plus a2 prime e to the 2 pi ix over a plus blah blah blah. That is the first series, right? And the second series is b0 prime plus b1 prime e to the minus I pi x over a plus, excuse me, b2 prime e to the minus 2 pi ix over a plus blah blah blah, right? So instead of that, if you look at the boxed equation, if I write the boxed equation, f of x equals, now n goes to minus infinity to infinity, so it will have terms like c0 plus c minus 1 e to the minus I pi x over a plus c1 e to the I pi x over a plus c minus 2 e to the minus 2 pi ix over a plus c2 e to the 2 pi ix over a plus blah blah blah, right? But if you look at the equations term by term, you would find that a0 prime plus b0 prime can be identified with c0, right? a1 prime is the same as c1, B1 prime is the same as C minus 1. A2 prime is the same as C2. And B2 prime will be the same as C minus 2 and so on and so forth. So these two are the exact same series. So instead of looking at two different series with positive n summed over, we can have just one series with n running from both negative and positive integers. That is what I'm saying. Is that okay?
Yes, sir.
All right. So I'll erase this part. Any other questions? So notice that the periodicity of f of x is inbuilt in this formula because f of x plus 2a, if I compute, this is equal to n equal to minus infinity to infinity Cn e to the in pi over a x plus 2a. So this part is equal to e in pi x over a times e to the in 2 pi. And e to the 2 pi in is always equal to 1. So f of x plus 2a is the same as f of x plus a. Now, this is all well and good. We can always express this, but the whole thing can only be meaningful if you can figure out what the expansion coefficients are, right? So this is actually, on the face of it, this looks very troubling because you have some function, let us say something that looks like this or whatever it is, right? Whose value is the exact same thing after you move forward by an amount. And I am writing this as an infinite sum of all possible exponentials. So I need to figure out a way to fix all these coefficients such that the graph of the right hand side is the same as the graph of the left hand side. This seemingly very difficult problem is actually made possible because the e to the I pi x in a language of linear vector space are basis functions. In other words, if I integrate from minus a to plus a, 1 over 2a, that is the width of this integral, dx e to the minus I m pi x over a e to the I n pi x over a. This is a Kronecker delta m and n. And I think this you have verified in a previous tutorial problem, if I'm not wrong. Do you guys remember this? Or should I prove this to you? Bolo. Okay, so I'll take silence to be agreement. And I will assume that you guys know about this. If not, it might be a good idea to work this out and try to satisfy yourselves that this is indeed true. Okay. This is basically the same statement that EMEN is delta MN, right? Where your basis vectors are the e to the in pi x over a's. So using this, I can simply figure out what the CNs are. The CN is, suppose if I multiply the boxed equation, which I will call equation 1, I'll multiply this by e to the minus I m pi x over a on both sides. So e to the minus I m pi x over a f of x equals n equals minus infinity to infinity Cn e to the I pi x over a times n minus n. And now I will integrate both sides. I'll multiply by 1 over 2a minus a to a minus a to a 1 over 2a dx. Okay. Now notice that the right hand side is nothing but the e to the I pi x over a n minus m dx 1 over 2a integrates to delta nm. So this is n equals minus infinity to plus infinity Cn delta mn. So out of this infinite sum, you pick out only one term for which n equals m. So this is equal to Cm. So using the orthogonality of the expansion functions, I can figure out my expansion coefficients. And this is nothing new to you. You have done this many times in quantum mechanics thus far before. And I have a formula for Cm. This is equal to 1 over 2a minus a to plus a e to the minus m pi x over a f of x dx. And I will box this guy also because I want to connect these two guys to the Fourier transform and the inverse Fourier transform. So this is equation 2. So are equations 1 and equation 2 clear to all of you? Notice that in equation 1, I didn't have to choose plus I n pi x over a. I could have also chosen e to the minus I n pi x over a. It would have been the exact same series. But if I had chosen e to the minus I n pi x over a, equation 2 should have been e to the plus I n pi x over a. Because to exploit the orthogonality, I need a difference between the two integers, not the sum. So if I had chosen e to the plus I n pi x over a in equation 1, I have e to the minus I n pi x over in equation 2. But if I had started with e to the minus I n pi x over in equation 1, equation 2 would have had e to the plus I n pi x over. Okay. So this is the theory of Fourier series. Fourier series basically tells you that if you have any periodic function of any variable, you can always express this as a series of either cosines and sines or e to the ix's, and the expansion coefficients can be figured out using a formula like equation 2. Okay. In your original study of Fourier series, this equation 2 might have been a little mysterious. But in the language of vector spaces, equation 2 is not at all mysterious because you understand the e to the I n pi x over a as a basis function in some space, and equation 2 is simply the expansion coefficients by exploiting the orthogonality of the basis functions. Okay. Now, my job now is to try and extend this to a continuous system. Okay. So suppose if instead of looking at a discrete system with n to be discrete, what will happen if I make k a continuous variable? Okay, so let us look at the crucial point. Kn is n pi over a, right? Now n is a discrete number. So if I go from one value of n to the next value of n, I change n by one value, right? So delta n is n plus 1 minus n, which is just 1. Okay. Correspondingly, delta kn as I change n would be n plus 1 pi over a minus n pi over a, kn plus 1 minus kn, which is pi over a. So in the variable n, everything is discrete, but delta k is n independent. Okay. Which tells me that if I make a larger and larger and larger, I can make the difference delta k smaller and smaller and smaller. So what am I doing here? What I'm trying to understand is if I make the k a continuous variable, remember that if kn is strictly discrete n pi over a, then I can only go from one k to the next k where the difference in these k values is pi over a. So the k values between n plus 1 pi over a and n pi over a are inaccessible to me. Okay. But now I don't want that anymore. I want all values of k to be accessible. I want this to be a continuous variable. If I want this to be a continuous variable, then I have to make a larger and larger and larger. So delta k can be smaller and smaller and smaller. If I make a very, very large, then I can make delta k as small as possible so that I have access to all possible values of k. In effect, I change delta kn to a continuous differential dk by taking the limit a goes to 0. So I am interested in the limit delta k n goes to 0, which is the same as the limit a goes to infinity. And in this limit, so I'll write the function f of x again. F of x I can write as n. I will not write the limits every time. Oops, this is not showing up. So I'll stop share and reshare again. Sorry about that. Okay. So I will not write n equal to minus infinity to plus infinity. That is sort of understood now. Cn e to the I n pi x over a. and I will simply multiply this by delta n. There is nothing wrong with multiplying by delta n because delta n is just 1. So I'm multiplying by 1. Now I will do a small trick, and I will, instead of looking at a sum over n, I will try to look at a sum over kn by multiplying and dividing by a over pi. N Cn e to the I n pi x over a pi delta n over a. Okay. So all I have done is multiply by a over pi times pi over a, which is just 1. But I can recognize that this guy is just delta kn. So I can write this f of x as a over pi sum over n Cn e to the I n pi x over a delta kn. Okay. Or I will write this as a Cn over pi e to the I n pi x over a delta kn. So far so good. Does anyone have any questions? This is just very simple manipulations. So I'm not doing anything very complicated. Okay. Now I will do a change of variables, and I will call a Cn over pi as some other function of n, which I will call g of kn over square root of 2 pi. I can always do this. Okay, instead of calling it by one constant Cn, I'm going to call it by different constant g of k. So I'm going to write my f of x as I'll pull out the 1 over root 2 pi sum over n g of kn e to the I n pi x over a delta kn. And now I will take the limit a goes to infinity. If I take the limit a goes to infinity, as we have argued before, k becomes a continuous variable. So I can replace the sum over n by an integral over k. This is actually strictly speaking a sum over kn, but it is equivalent. So the sum over kn becomes integral over k, and n goes from minus infinity to infinity simply means that the continuous variable k goes from minus infinity to plus infinity. And in this limit a goes to infinity, delta kn becomes a continuous differential dk. So I can write this as dk. This becomes a function of the continuous variable k, and e to the n pi over a, which is kn, now becomes a continuous function k. Make sense? Are there any questions about this generalization? As I go from the formula on the first page to the formula on the second page, excuse me, I have taken the limit a goes to infinity. Once I take the limit a goes to infinity, then my k becomes essentially a continuous variable. So my function f of x can be written as that particular integral that I have written down as an integral over k. But notice that in this whole bargain of making k a continuous variable, I have lost something. What I have lost is the periodicity of f of x. So this is not just applicable to periodic functions anymore, because if you now compute f of x plus 2a, this actually is meaningless because a is now infinity. So this means that I'm actually talking about a function which is periodic, but the period is infinity, which means if I want to see the same functional value repeating again, I have to wait for an infinite amount of space, which is not really practical. So what I'm essentially saying is that this is a non-periodic function. So this formula, which I will again box because this is important. And I'll call this equation 3 is called a Fourier transform. So G of k is called the Fourier transform. Okay. The difference between Fourier transform and Fourier series should now be obvious. Fourier transform is a summation over a discrete index n, where the periodicity of f of x is manifest. In fact, it is only applicable to functions that are periodic. But if you extend this to a continuous system, it is valid for non-periodic functions as well. So I can extend the notion of Fourier series to the notion of Fourier transforms, wherein I can apply it as a representation of any function f of x, regardless of whether it is periodic or not. In fact, the periodicity is not at all apparent by looking at the equation number 3. Okay. So this is essentially the mathematics of Fourier transforms in about half an hour. Now I have to understand how to determine the coefficients g of k. But remember that my g of k I have gotten by this identification, right? This identification. So what is my g of kn? G of kn is basically a over pi times square root of 2 pi times cn. But I've already figured out what cn is, right? This is equal to a over pi square root of 2 pi. My cn in the discrete case is given by formula number 2. So let me write down formula number 2. It's 1 over 2a integral minus a to plus a dx e to the minus I n pi x over a f of x. Now again I will take the limit a goes to infinity. Notice that in the overall coefficient outside, the a cancels, this a cancels this a. So if I take the limit a goes to infinity, again k becomes a continuous variable. So g of k equals, there is a square root of 2 on the top and a 2 on the bottom. So that becomes a 1 over square root of 2 pi at the bottom. And if I take the limit a goes to infinity, this becomes minus infinity to plus infinity dx. Now n pi over a is the discrete index kn, which means now it is the continuous index minus ikx f of x. So these expansion coefficients, which I will call as formula number 4, can also be obtained by taking the continuous limit of equation number 2. Okay, and this formula is called the inverse Fourier transform of f of x. If f of x, g of k is the Fourier transform of f of x, then f of x is the inverse Fourier transform of g of k, or the other way around also. People say it whatever you want. So if 3 is the Fourier transform, 4 is the inverse Fourier transform. Okay. So somebody asks, I didn't get how they can be used for non-periodic functions. Well, they can be used for non-periodic functions because if you look at formula number 3, what is the periodicity of f of x? There is no periodicity of f of x, right? If I put f of x plus 2a, then I don't get f of x plus 2a equal to f of x. It is not periodic manifestly. It is not periodic because I've taken the period to be infinity, right? If you take the period to be infinity, then for the function to repeat itself, it takes the entire length of space, which means it's essentially non-periodic in the entire interval minus infinity to plus infinity. So that is what I mean by saying f of x is non-periodic in this case. Okay. So equations like 3 and 4, which are the Fourier transforms, can be understood as the extension of the idea of Fourier series to the case of a continuous system, or equivalently a non-periodic functions. And this is the stuff that we'll be using over and over again. Questions? Questions or comments? Okay. So we're done with that. Again, this is not sharing, so I will stop share and reshare. Sorry about that. So let's come back to our original problem. What was our original problem? We have written down some functions. So if you go back to the free particle case, okay. So we have written down some function psi of x as 1 over root 2 pi minus infinity to infinity dk g of k e to the I kx as a linear superposition of waves. Where are the waves? The waves are the e to the I kx's in this formula, right? This is the wave part. And where is the linear superposition? These are the expansion coefficients. The difference is that the expansion coefficients g of k are now functions of k. Okay. In the Fourier series case, the expansion coefficients were just an and cn, which were constants. But in the Fourier transform, the expansion coefficients g of k and f of x are not constants. They are functions of either k or x. Okay. And this is important to understand because if I want to construct something that is localized in space, I cannot simply add 1 times sine k1x plus 2 times sine k2x and things of that sort. I would not get anything that is localized. I would still get a delocalized wave, but I should make the expansion coefficients also k-dependent functions. Now, if I choose g of k's carefully, then my hope is to try and understand something that looks like a wave packet. Okay. So let me give you a canonical example of a wave packet. A canonical example of a wave packet is basically a Gaussian. So suppose if you talk about a Gaussian, again, wrong color, Gaussian. What is a Gaussian? Psi of x is some normalization times e to the minus x minus x0 whole square by 4 sigma square. Again, don't read too much into the 4 sigma square. I can as well call this sigma square or 2 sigma square or whatever it is. My normalization n will change accordingly. That is all. How will I fix the normalization? I'll fix the normalization by requiring that minus infinity to infinity psi of x square dx is 1. Because psi of x square dx is a probability of finding the particle in some interval dx. Since I should find the particle somewhere in the universe, I should have the whole wave function normalized. And you can easily show that this would give you n square equals 1 over sigma times square root of 2 pi. If you have not done this calculation, you should verify that this is what the normalization constant will be for this particular problem. Okay? Now, why am I talking about a Gaussian? Because I can think of the Gaussian as representing a wave packet. So what does this mean? A Gaussian obviously is something that is delocalized that looks like this. So this particular Gaussian, for example, so it goes to 0 as x goes to plus minus infinity, right? And it has a maximum value at x is equal to x0, right? The way I've constructed the Gaussian, the maximum value of this function is at x is equal to x0, where psi of x at x is equal to x0 is basically just n, right? So in other words, psi of x mod square is maximum at x equals x0, and this maximum value is just normalization squared, and psi of x mod square falls to 0 as x goes to plus minus infinity. Now imagine that you're shrinking this Gaussian. Okay, so you put pressure on both sides, you take your two hands and squeeze this graph. If you squeeze this graph, you're going to get something that looks smaller and smaller and smaller, but taller and taller and taller. Okay, so you can have an infinite wave packet localized at x is equal to x0. And this is how you understand, for example, a delta function, eigenfunction. So when I say, so to answer the initial question that was raised, qualitatively, this is how you understand it. Of course, I cannot have the delta function as a physical eigenfunction, but I can have a Gaussian as the physical eigenfunction of any particle, because a Gaussian is a perfectly normalizable function. It lives in the Hilbert space of P infinity, and I can perfectly well take Gaussian to be the physical eigenfunction of any system. In fact, you will actually see an example of this when we talk about some examples of one-dimensional problems. Now, if I squeeze a Gaussian, the Gaussian is still a Gaussian, right? Of course, what changes is roughly speaking, the width of this graph changes, right? Suppose if I go from here to here and I call this the width, I'll qualify very carefully what I mean by the width. But if I keep squeezing it, the width goes smaller and smaller and the graph goes taller and taller. And if I keep squeezing as much as possible, I can finally get something that looks like this. I can get something that looks like this. Okay, I mean, I cannot draw it absolutely correctly, of course. Okay, this is x is equal to x0. Now, what is the difference between the first one and the second one? The second one is also a Gaussian. But if you keep shrinking the Gaussian, it starts approximating a delta function, right? So I can very well claim that this particle is an eigenstate of position because I'm making the value of position as close to x0 as possible. So this is the sense in which you understand position eigenfunctions. Even though, as someone of you correctly pointed out, that these are not physical functions that can serve as wave functions of some particle because these are not normalizable. I can think of some other function whose limit looks very much like the delta function, but this original function is a perfectly normalizable function. Okay, I can also think of the momentum eigenfunction in a similar fashion. I can think of a momentum space. So in quantum mechanics, equation number 3 is the position space wave function of a particle, and equation 4 is the momentum space wave function of a particle. So what I'm essentially saying is that if f of x is a Gaussian, then g of k is also a Gaussian, because this is something you proved in the tutorial, and we will sketch this very quickly in this class also. So you can think of functions of either k or x that are highly localized, but there is a trade-off. If I localize the position space eigenfunction and I make the uncertainty in the position space as small as possible, then correspondingly there will be a very large spread in the momentum space eigenfunction and vice versa. This is the uncertainty principle, and we'll come to this in a second. But before I come to this, I have to make this point about width a little more specific. Okay. So let's push ahead and calculate the momentum space eigenfunction also. So notice a very beautiful property about these Fourier transforms. Okay. So let us say that I have psi of x. Okay. And then I construct the Fourier transform of psi of x. So this is some g of k, which is equal to 1 over root 2 pi minus infinity to infinity dk e to the minus ikx psi of x. Okay. Now let me assume that psi of x is normalized. Okay. In other words, so psi of x times assume psi of x is properly normalized. Okay. Then you will go home and show, then you can show that excuse me, g of k is also normalized to unity. You don't have to do anything extra. If you have constructed psi of x that is properly normalized, then the Fourier transform of psi of x, which is g of k, is also normalized, and you should show this. Since I've written it in blue, and our convention is that anything I write in blue, you should go back and think about and solve on your own. Okay. All right. So where was it? So let me go back to phi of k. Phi of k or g of k, whatever we call it. G of k for a Gaussian. For a Gaussian, this is equal to 1 over root 2 pi minus infinity to infinity dx n e to the minus x0 square over 4 sigma square times e to the minus ikx. Okay. Now we proved, I think in the tutorial number 5, that this function on the right hand side is also a Gaussian. The way you do it is by first doing a change of variables to x prime equals x minus x0. So your g of k becomes 1 over root 2 pi. And you can pull out a factor of e to the minus ikx0 minus infinity to infinity. And I can also pull out n dx e to the minus x prime square over 4 sigma square e to the minus ikx prime. Okay. And then you complete the square. And then finish the integration. So this is something I have shown in detail in the last video. I will not repeat it here. But if you do it correctly, ultimately you will end up with a momentum space eigenfunction that is given by n square root of 2 times sigma e to the minus ikx0 e to the minus sigma square k square. Okay. Again, if you're unsure of how I got from the previous line to this, all I did was complete the square and make this into a Gaussian integral again, and then simply wrote down the answer. The answer would be a function of k square, which means if psi of x is a Gaussian function of x, then g of k is also a Gaussian function of k because it goes like e to the minus sigma square k square. Now you might object because there is a minus ikx also, minus ikx0 also there. But that is all right because I can always complete the square and I can write this as some e to the minus a k prime square, which is a Gaussian of k. Okay. So let me write down these two formulas separately. Psi of x is n e to the minus x0 whole square over 4 sigma square, which implies that mod psi of x square is n square e to the minus x0 whole square over 2 sigma square. Okay. And g of k is n root 2 sigma e to the minus ikx0 e to the minus sigma square k square, which means mod gk square is n square times 2 times sigma square e to the minus 2 sigma square k square. I think there is a question, so let me try to go to the chat. Shouldn't there be a dx prime in the integral? Yes, correct. So this is a dx prime. Thank you. Okay. Now I'm going to define the width of a Gaussian. Okay, this is the general accepted nomenclature for a width. Now let us look at the psi of x function. The psi of x function, the way we have written down, reaches a maximum at x is equal to x0 and then falls on both sides. Similarly, the g of k function reaches a maximum at k equal to 0 and then falls on both sides. In other words, so instead of looking at psi of x and g of k, mod psi square becomes maximum at x is equal to x0. So let me look at what is the equation number. So let me call this equation 5 and equation 6. So psi of x0 is maximum at x is equal to x0, and g of k, the way I've written down, is maximum at k equal to 0. Okay. I can also construct it any other way if I want. I can make this 2 sigma square k minus k0 whole square, in which case g of k would be a maximum at k equal to k0. Okay. Anyway. And then after x changes from x0, the function psi of x falls. So I will define my width in the following fashion. I will say that the width of the part, so here I should compute the width of this Gaussian, which means I should first ask myself if I should go from this point to this point, or maybe from this point to this point. This has a smaller width, or maybe from this point to this point, which is the width. So there should be some mathematically accepted definition of what the width of the Gaussian is. So the mathematically accepted definition is this. Let us say that you have the maximum at x is equal to x0. Then where does psi of x prime, psi of x mod square fall to e to the minus 1/2 of its maximum value. Okay. In other words, I want to find out the point psi of x prime mod square such that psi of x prime mod square divided by psi of x0 square is e to the minus 1/2. Psi of x0 mod square is basically where the function is maximum. So substitute this in the formula for psi of x square. So this is equal to n square e to the minus x prime minus x0 square divided by 2 sigma square divided by, so at x is equal to x0, this is just n square, and this has to be e to the minus 1/2. Okay, which means x prime minus x0 square divided by 2 sigma square has to be 1/2, which gives me x prime minus x0 modulus of this is basically sigma. So the way I've defined it, so this is basically the spread I will call delta x, which is equal to sigma. So I will define the width of the Gaussian as that point x prime at which the intensity of the Gaussian falls to e to the minus 1/2 of its original value. Now, if I use this definition for the position space eigenfunction, I should use the exact same definition for the momentum space eigenfunction. So the momentum space eigenfunction reaches a maximum at k equal to 0. So I have to calculate that value of k prime for which the intensity of the momentum space eigenfunction compared to its value at the maximum value of k is e to the minus 1/2. Which means that if you look at the formula for momentum space eigenfunction, this is 2n square sigma square e to the minus some 2 sigma square k prime square divided by 2n square sigma square times e to the 0, which is 1. This has to be equal to e to the minus 1/2, which tells me that 2 sigma square k prime square is 1/2, or k prime modulus is, what is it, 1 over 2 sigma. Okay, so this is basically the spread in the momentum momentum space eigenfunction, which means if I construct this as the wave packet of a physical system, then this extent of uncertainty in either position of the particle is given by sigma. If I localize the position space eigenfunction such that this delta x is as small as possible, okay, which means I squeeze this Gaussian more and more and more and more and more, so I make sigma as small as possible, which means I make the spread in position as small as possible, then the corresponding spread in the momentum space eigenfunction is as large as possible, because that guy goes like 1 over sigma. Okay, so this is basically Heisenberg's uncertainty relation. Delta x times delta k, in this case of Gaussian, is equal to sigma times 1 over 2 sigma. If I multiply this by the quantity h bar, and h bar times delta k is basically my uncertainty in momentum delta p, then I get delta x times delta p equals h bar over 2. So remember that Heisenberg's uncertainty principle tells you that delta x times delta p has to be greater than or equal to h bar over 2. So the Gaussian is a special kind of wave function which saturates this bound. So the uncertainty in position times the uncertainty in momentum has to be greater than a very minimal quantity, which is h bar over 2. And the Gaussian attains the most minimum value possible. So for this reason, the Gaussian is called the minimum uncertainty wave packet. Okay. Now this relies on the definition of width to be e to the minus 1/2 of the original value, and I simply argued qualitatively that you can constrain the particle to be within this wave packet, and you can make the position as small as possible by squeezing the Gaussian, in which case the uncertainty in its position is at most the width of the Gaussian. Okay. And the uncertainty in position, momentum becomes 1 over the width of the Gaussian in some units. So the uncertainty principle is satisfied. The way you actually properly show this is by computing the delta x and delta px properly quantum mechanically. So this you would do. So what should you do? Take psi of x as n e to the minus x0 whole square divided by 4 sigma square. Okay. And then calculate the expectation value of the x operator, expectation value of the x square operator, expectation value of the p operator, and expectation value of the p square operator for all these guys. How would you calculate the expectation value of the x operator? Remember that x operator expectation value is psi x psi, right? So I can write this as integral dx prime psi x prime psi, and this is nothing but delta of x minus x prime, and this is nothing but the wave function psi of x prime. This is nothing but psi star of x. The inner product of x prime and psi is psi, so the complex conjugate of this guy is psi star. But I can use the delta function to do one integration. So my expectation value of x is basically equal to minus infinity to infinity dx psi star of x psi of x. Okay. And you can also show that the expectation of momentum is basically minus infinity to infinity dx psi star of x minus IH bar ddx of psi of x. And p square is minus infinity to infinity dx psi star of x minus IH bar ddx square psi of x, and so on and so forth. And then calculate delta x. So remember that delta x is x square minus x square, and delta p is p square minus average value of p whole square, and then show that for the Gaussian delta x times delta p is equal to h bar over 2 using these definitions. Okay, this is your homework, and take this very carefully, and don't do the integrations over and over again. Please refer to the problem that we have done before, where we have actually shown, for example, minus infinity to infinity x e to the minus x square over sigma square dx would be equal to 0, because x is an odd function and e to the minus x square is an even function. So if you have these things, you can simply use. So some Agnivo says there will be an x prime delta x minus x prime. This is x prime delta x minus x prime. Thank you. Can you explain the second step you did? I couldn't recall that. I don't know what second step you refer to. So if you can tell me which step you are referring to, I can explain that. I'm sorry. Anyway, you can use all these integral formulas that we have developed in a previous tutorial. So instead of the way I have shown the uncertainty principle is one way to calculate it. And the exactly correct way to compute it is to simply calculate the expectation values of x, x square, p, and p square, and then show that the uncertainty times x times uncertainty p is h bar over 2. Okay, so take this exercise seriously and do this. And this is how we approach the free particle in quantum mechanics. You basically construct a wave packet and assume that the particle can be constrained to lie within the wave packet. And the way you construct the wave packet is by adding a whole bunch of waves. In fact, infinite number of waves, a linear superposition of an infinite number of waves with k-dependent coefficients. Of course, all these waves are adding up in some weird fashion to give you something that looks localized in space. Okay. Now, of course, I cannot choose all these waves to be exactly the same. They should have some differences. And then once I set this wave up, it should start propagating, right? I should put in a time dependence. So we will discuss briefly how the wave packet propagates in time in the next lecture. But for this lecture, I will stop at this point, and I will again request you to take this homework and the anything in blue seriously and work this out yourself, so that you become conversant with the workings of quantum mechanics. And this is quite important as we move along. So the next lecture, I will talk about the time evolution of the Gaussian wave packet, and then we'll move on to a general analysis of potential problems, one-dimensional potential problems in quantum mechanics. I'll make some general remarks about bound states and scattering state solutions, and then we will move on to the harmonic oscillator. I will not talk about the box problem, potential in a box problem in the class, because I'm almost certain that every one of you has seen this before. So that will be relegated to a tutorial problem. But I will discuss the harmonic oscillator in detail, and then I will talk about the scattering matrix and transfer matrix and set up the basics of scattering in quantum mechanics. But we will take up the issue of scattering more seriously in the next semester. Okay, so that is the rough plan going forward. But before all these things, I will also squeeze in some remarks about the Schrodinger picture and the Heisenberg picture before I talk about specific one-dimensional problems.